Hey, what's up? It's your old pal, Mr. Cook, and we are going to get started on this review. So, for AP Calculus BC, it's the Unit 1 review. It's our very first test of the year. We start off with finding the limits. Then we go to showing a limit based off of a graph, and evaluating a limit, like the different parts and continuity after that, intermediate value theorem, and then rounding off with asymptotes. So I think in the first video, we're just going to go over like maybe the first 6 limits. So yeah, we'll just go through a couple at a time, and I'll try to keep the videos relatively short and sweet. Okay, I'm going to try my best not to do any work with a calculator here. I'm just going to try and factor when I can, and then use a lot of the limit properties that we have during all of this. Now, remember that this test is a non-calculator test, so that means that's actually good news for you. It means if you have a graph, the graph is going to be given to you, which is fantastic. And if you have to do any computational stuff, it's going to be very basic computations. Okay, so anyways, let's get started. So number 1, we got the limit as x goes to 3. Whenever we do a limit, we want to check the left and the right hand limits, obviously. However, sometimes if you have like a just continuous function that you know is going to work, you can just plug numbers in. After that, if you can't plug a number in, if you end up with like some weird result like 0 over 0, infinity over infinity, anything like that, you can use some of those like fringe rules if you know them, like L'Hopital's rule, stuff like that. But typically we like to just use some algebraic steps like factoring or multiplying values in the numerator and denominator to simplify an expression before evaluating it. Then you go right back to the regular part, just plugging in. Occasionally you're going to have to use memorized rules, like number 5, for example. That's going to require a memorized rule. Same thing with number 4. They're called transcendental methods of finding the integral, or the limit. So we're going to work with those first. Okay, so we're going to start with number 1. Number 1, limit as x goes to 3 of the square root problem. So I'm going to just try plugging it in. So if I do plug it in, what I get is 3 plus 1 and the square root, and that's square root of 4, which is 2. So 2 would be my limit. I just have to plug it in, and that's it. That's all the work you have to show. Maybe not even that. I think you could probably get away with if you knew it in your head. Just writing, equals 2. That'd be fine. Okay, so if I try to plug in -4 here to the numerator, x minus 4 give me a 0 in the numerator, and then if I plug in the bottom, -4 squared is 16, and then plus 20, that'd be 36, and then 9 times -4 is -36. So we get 0 over 0. Some of you guys might recognize that from, Calc AB, where you can use L'Hopital's rule. So just fill out the rules for L'Hopital's rule. I'm not going to try and teach that right now because we're going to learn it a little bit later. So instead, what I'm going to do is just show you the algebraic method to solve this out. So when you get 0 over 0, sometimes, especially when you're working with rational functions like this, excuse me, it means that you can factor out an expression. So that's what I'm going to do. I'm just going to use, for an algebraic step, factoring the quadratic in the numerator and the denominator. Okay, so here we go. If I do that, I get x plus 4 on the top. And then in the bottom part, if I take x squared plus 9x plus 20, if I factor that, numbers that multiply together would be 20, add together would be 9, that'd be 4 and 5. So x plus 4, x plus 5. And you'll notice real quickly that x plus 4, it'll divide out of the expression. Okay, so then if we do that, then we get the limit as x goes to -4 of just 1 in the numerator, and then x plus 5 in the denominator. And then if I plug in again, I get 1 over -4 plus 5, and that'll give me 1 over -1, 1 over 1, which is just 1. Okay, and so there's my limit for that one. It's just going to be 1. All right, so there we go. Just make sure that when you do, before you plug in the -4, when you formally plug it in, make sure that you include, after you write the equal sign, that limit expression. If you don't include that, we'll probably take a point off. And you know why we do that? It's because AP would also do something like that. So make sure that you keep writing that limit expression until you finally do plug that -4 into the expression. Then you can just get rid of it. Notice that the limit just disappears over here. It's because I had plugged in -4, and I don't need the limit anymore because I plug it in, or limit notation. Okay, number 3. So same kind of thing. We just factor this. So, man, I'm going to have to dig deep on this one because of that factored expression. But I know that if I plug in -3 to the top, I would get -27 plus 27, which would be 0. And then if I plug in the bottom, -3 plus 3 is also going to add up to 0. So if I just plug in, that's not going to work. So what I'm probably going to have to do is an algebraic step, and that would probably be factoring again. So I have a feeling that x plus 3 is going to factor out of this expression. And I'm pretty sure that that's a perfect cube. Yeah. x to the third plus 27. So that's the same as saying a to the third plus b to the third. I'm pretty sure this one factors in the following way: a plus b, and then I think it's a squared minus ab, and then plus b squared. I think that's right. Let me just double check that real quick. So if I distribute the a in there, then I would get a to the third, and then a times negative ab would be negative a squared b, and then let's see here, and then a times b squared would be plus ab squared. And if I took the b times a is a squared times b, which cancels out over here. And then b times negative ab would be a negative ab squared. And then b times b squared would be a positive b squared. And it looks like that's going to cancel that. Yeah, so I do end up with a to the third, b to the third. So that's good. So this is like the one of the things that you can memorize. It's the difference of cubes, or actually sum of cubes. And so that means that if, let's see, from this one, if x is a and 27 is 3 to the third, so 3 is b, and that means that this part will factor to become this, okay? So that's what I'm going to use. I'm going to use that rule. So let's start off with a plus b. So that'd be x plus 3. And then a squared is x squared, so x squared minus, and then that would be 3 times x, so 3x. And then that one's going to be a plus 3 squared, which is 9. Okay, so now notice again that I have this x plus 3 here. That'll cancel or divide out in the top and the bottom, leaving me with the limit as x goes to negative 3. And then the numerator is just going to be x squared minus 3x plus 9. Now if I plug in negative 3, I get, let's see here, negative 3 squared minus 3 times negative 3 plus 9. So that'd be 9, and 9 is 18. And then 3 negative 3 squared is 9 again. So I think that's going to be 27. I don't know. You can honestly just kind of leave it like this if you don't want to do the computation in your head. And that's good enough, because I know that's just going to be some numbers. So that's the limit right there. Okay, number 4. This is one of our transcendental limits. Let me just do a brief kind of recap of the transcendental limits. There's one that looks like this: the sine of x over x, and that's the limit as x goes to 0. What happens is that this is going to end up being 1, and you can just memorize that. And same thing with the reciprocal. And why would the reciprocal work? Well, if this ends up being 1, that means the numerator and the denominator are the same. So that means that I can swap it around as well. And it ends up being true that you can actually multiply any coefficient on the x value as well, so long as that coefficient also stays, as the input value also in the numerator or the denominator. So just remember that you can also have any coefficient on that x value as well. But either way, it ends up being 1. The other one that you want to memorize has to do with cosines, and that'll show up over here. It looks something like this. If you have the limit as x goes to 0 of 1 minus cosine of x over x, and then similarly the limit as x goes to 0 of cosine of x minus 1 instead over x. These are both just going to become 0. So the reason why is because you can move the fraction apart, and basically it ends up canceling out. The terms are basically going to be the same. Should I show why that is? Okay, so if you split this fraction apart, you get 1 over x and cosine of x over x. And the thing is that cosine's largest number is 1, right? So that's why if you subtract them, basically this ends up being the same thing. So that's why this works out really nicely. All right, so these are the transcendental limits that you can memorize for this for these types of problems. I think that we made a pact not to put this on the test, so you don't have to know the transcendental limits unless you don't have a calculator. And we don't have a calculator, but I don't think that we have much representation of these problems on the test. So, but knowing those is really helpful, and I'll show you how to use them in numbers 4 and 5, and then also number 8. So that's where we're going to use these. And in fact, you know what? That's what I'll do. I'll finish up by doing 4 and 5 and 8 for this video. So for number 4, if I use that rule, limit as x goes to 0 of the sine of cx over cx equals 1, then I'm pretty close to getting that here. What's the one thing that I'm missing? It looks like I got the sine, I got the x in the denominator, but it's got to be a 3x, right? Because this has to be the same as this part for this to be equal to 1. So I'm missing a 3. So here's what I'm going to do. I'm just going to use an algebraic step to get that extra 3. Okay, so as x goes to 0 for this limit. The sine of 3x goes right here, and I can't take that 3 out or anything like that. I've got to leave it in because it's inside of a function. It's a composition. So I'm going to put an x here and also a 3. But these aren't technically equal to each other yet, because I've added in a 3 in the denominator. So the way that I'm going to keep this equal is by moving another 3 into the numerator. Now what happens is I can just group this together. This part is like this pattern, so it's going to become a 1. But I still have that little 3 right there. So this is going to become, with this limit right here, okay, it's just going to have a 3 by itself. And then when I take the limit of this stuff, it just becomes a 1. So 3 is going to be my answer overall. So I just used this little rule here with this like part of the limit, and I was able to get the answer for this. Okay, so next up, I'm going to do number 5. So number 5, same idea. I'm going to use the transcendental limits, but I'm going to use that tangent and turn it into those. Okay, so one of the things that you can do is use the fact that the tangent of x is equal to the sine of x over cosine of x. And you can use this relationship to then rewrite the tangent expressions into something simpler. And that's what I'm going to do in this problem. And when we do that, you're going to end up seeing like why things end up being kind of bad. Because like if I were to just plug the numbers in, 0, for example, I would get tangent of 0 over tangent of 0. And the tangent of 0 is 0. So that's a 0 over 0 situation. So you can't really plug it in. So we're going to have to use some different means. And that's when using a trig identity is going to help out in this case. So we take the limit as x goes to 0. If I take that 5, I'll take that 5 out of it. And let's just work on the tangent. So tangent ends up being the sine of x over the cosine of x. Okay, and then over that, we're going to put this other tangent, and that's also sine over cosine. But since we have a 3, it's going to become the sine of 3x over the cosine of 3x. All right, now, algebraically, what happens is that, with these values, right, I've got a fraction in the denominator. When I divide by a fraction, it's the same as multiplying by the reciprocal. So now I'm just going to move this up into the numerator and see what I got. So then this turns into limit as x goes to 0. Then I have 5, and then I've got that sine of x and the cosine of x. And then it's going to be multiplied by the reciprocal of this fraction, right? So the cosine of 3x over the sine of 3x. There we go. Okay, and now if I plug in 0, now you're going to see why this ends up being really bad. Because if I plug in 0, sine of 0 is 0. Sine of 3 times 0 is going to be 0. So that means that that's where I get the 0 over 0 from. It's from these stupid sines right over here. So I got to figure out a way to get rid of the sine parts. And that's where this transcendental limit comes into play again. So this pattern comes into play. So here's what I'm going to do. I'm going to separate these fractions apart first. So if I do that, I get the limit as x goes to 0. I get that 5 right there. And then I'm going to write sine of x over cosine of x like this. I'm just going to split it apart. So sine of x over 1 times 1 over the cosine of x. Okay, and then similarly with the other fraction, I've got a cosine of 3x over 1. And then, the last part is 1 over the sine of 3x. Like that. Okay, now to use the transcendental limit, I need to follow this rule. I need, the same thing as the input. It also needs to be in the denominator or in the numerator, opposite side of the fraction. So I need an x in the denominator here. So that's what I'm going to do. I'm going to put an x in the denominator. But remember, this equal sign is really important. So if I put an x in the denominator like I just did, I also got to put one in the numerator. So I'm just going to strategically put one right over here. Okay. That keeps everything the same. We're all good. We're using a limit evaluating to 0, so not actually 0. So I haven't broken any rules by doing this stuff, okay? All right, and what's great about it is that when I pair the limit with this expression right over here, sine of x over x, this just becomes a 1, which is really cool. So now I'm dealing with this 5 and then this 1 here. And if I keep moving along, if I plug in 0 to this expression over here, cosine of 0 is 1. So this becomes 1 over 1. And then if I plug in 0 to this, 3 times 0 is 0. Cosine of 0 is 1. So that becomes 1 over 1. And then there's this last part. And you know what? Darn it. It's not exactly what I want. It's kind of like the transcendental limit, but I need, a 3x in the numerator. Well, I've got the x, so all I got to do is make a 3. So I'm going to put a 3 right there. But when you put a 3 in the numerator, you also got to put one in the denominator. So I'm going to put a 1/3 right over here to cancel that 3 that I added in out, keep everything the same, right? So this thing ends up becoming a 1 also because of the transcendental limit that we learned about earlier. And then I've got that 1/3. So then if I multiply all this stuff together, I just get one number, right? It's going to be 5 times 1 times 1 times 1 times 1 times a third, which is 5/3. So 5/3 is going to be our limit for that problem number 5. Okay, so there we go. That's number 5. Now let's move on to this last one for the video, which is number 8. And then, I'll do a separate video going over those last couple of limits, number 6, number 7, and number 9. Okay, so for number 9, I think you might be able to see it right away. Yeah, that 1 minus cosine of x over x, that's just going to be 0. Well, first off, let's try and plug it in. Okay, let's see what happens when we plug in 0 for x. We would get 3 times 1 minus cosine of 0 over 0. And divide by 0 is already bad, right? But we get 3 times, and then it's going to be 1 minus cosine of 0, which is 1. Oh, great. So we get 0 over 0 again. So that's obviously bad news. We've got to think of a different method. And that's where we use this transcendental limit. So if we use this part right here with the limit, remember that the limit as x goes to 0, the one that I talked about earlier, of 1 minus cosine of x over x ends up becoming 0. So like that whole part right over here just becomes 0. So it's going to be 3 times 0, which is just 0. So 0 is our limit for number 8. And that's about as easy as it gets. You just separate the 3 from it. Then it's exactly the rule that we're looking at. Okay, so hey, that's our first video. I hope you found this helpful. If you didn't, go track down your calc teacher. I'm Mr. Cook. If you need my help or if you want my help, I'm always available before school and after school. So come find me. I'll be somewhere around campus, and I'm always willing to help out. So I hope you found this helpful, and I'll see you in the next video. Bye-bye.